Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
All right, another week, another deep dive into the world of AI. Today's topic is something I've been following closely. Can large language models play text games well?
It's a loaded question, isn't it? What does play well even mean in this context?
Exactly. Are we talking about winning, or are we talking about understanding, or something else entirely?
I think that's a perfect starting point because on the surface, LLMs appear to be doing quite well at these games. You see headlines about them, mastering complex text adventures, solving puzzles, even exhibiting what looks like strategic thinking. But beneath the surface, I suspect there's something missing.
I disagree. I think it's remarkable. Just look at the advancements in recent years. We've gone from models that could barely string a coherent sentence together to agents that can navigate intricate narratives, anticipate consequences, and even, seem to role play. It's data, data, and more data. The more data we throw at these things, the more capable they become.
That's the crux of my skepticism. It seems like they're understanding, but is it real understanding? Or is it just incredibly sophisticated pattern matching? Are they really grasping the underlying logic, the causal relationships, the meaning of the game?
And I think that's a very astute point, because these text games are, in a sense, very limited worlds. They're confined to the textual domain. So, an LLM that excels in this environment might be very good at manipulating text, but does that translate to any kind of general intelligence, any ability to reason about the real world?
But isn't that how intelligence often manifests, initially? Through mastery of a specific domain. Think about humans learning a new skill. We start by memorizing patterns, mimicking experts, and gradually, over time, we develop a deeper understanding. I think LLMs are on a similar trajectory.
I'm not convinced. I see it more as a very impressive mimicry. They're exceptionally good at predicting the next word, the next sentence, based on the vast amount of text they've been trained on. But that's not the same as truly understanding the why behind those words. It's statistical association, not genuine comprehension.
Exactly. Think about a simple text game scenario. You see a goblin guarding a bridge. Do you attack, sneak past, or try to talk to it? An LLM can probably generate a plausible response for each option. But does it understand the motivations of the goblin, the potential consequences of each action, the overall strategic context of the game, or is it just regurgitating patterns it's seen in similar situations?
I think the key is in representation. How are these LLMs representing the game world, the characters, the actions? Is it just a big bag of words, or is there some kind of structured hierarchical representation? And if it's just a bag of words, how can it possibly reason about complex relationships and make nuanced decisions?
Well, the internal workings of LLMs are incredibly complex, but there's definitely structure there. The transformer architecture, with its attention mechanisms, allows the model to focus on the most relevant parts of the input text. It's not just a random jumble of words. There's a hierarchy of features being learned and processed.
I understand the architecture, but I still question the quality of the representation. Are these features truly capturing the semantic meaning of the text, or are they just statistical correlations? It feels like we're missing a crucial layer of abstraction, a way to represent concepts and relationships in a more explicit, symbolic way.
That's where I think neuro-symbolic approaches come in. The idea of combining the pattern recognition strengths of neural networks with the reasoning capabilities of symbolic AI. Instead of just feeding raw text into a deep learning model, we could try to extract symbolic representations of the game world, the rules, the characters, and then use those representations to reason about the game.
And that might help with the problem of generalization. Because if an LLM is just memorizing patterns, it's going to struggle when it encounters a new situation, a situation it hasn't seen in its training data. But if it has a symbolic representation of the game world, it can reason about new situations based on its understanding of the underlying principles.
But creating those symbolic representations is incredibly difficult. It requires a deep understanding of the domain, a way to translate natural language into formal logic. And even then, there's the problem of brittleness. Symbolic systems can be very sensitive to errors and inconsistencies in the input data.
That's true, but I think we can learn from the brain. The brain is incredibly good at integrating different types of information, at combining sensory data with abstract concepts. And it does this in a hierarchical way with different brain regions specializing in different levels of abstraction. Maybe we can build AI systems that mimic this hierarchical structure.
Exactly. Think about how humans learn to play chess. We don't just memorize a bunch of board positions, we learn the rules of the game, the value of the pieces, the strategic principles. And we use that knowledge to reason about new situations, to plan our moves, to anticipate our opponent's responses. That's the kind of intelligence we need to aim for.
And that raises the question of coordinate systems again. Chess is played on a two-dimensional board, but our understanding of chess involves more than just the spatial arrangement of the pieces. It involves concepts like control of the center, pawn structure, king safety. These are all abstract concepts that are mapped onto the physical board. And I suspect that true AGI will need to be able to translate between different coordinate systems like that.
Okay, but let's not dismiss the progress that's been made with LLMs. They're already capable of performing tasks that were once thought to be impossible for machines. They can generate creative text, translate languages, answer complex questions. And they're getting better all the time. I think it's just a matter of time before they reach human-level performance in text games.
I think the key is to focus on more than just performance metrics. We need to understand how these models are achieving their results. Are they truly understanding the game, or are they just exploiting statistical patterns? And if it's the latter, how can we move beyond that and build systems that have genuine understanding?
And that requires a more interdisciplinary approach. We need to combine insights from neuroscience, cognitive science, linguistics, and computer science to build AI systems that are truly intelligent. We can't just rely on brute force deep learning. We need to understand the underlying principles of intelligence.
I think we also need to be careful about anthropomorphizing these models. Just because an LLM can generate human-like text doesn't mean it has human-like understanding. We need to avoid projecting our own cognitive biases onto these systems and develop more objective ways to evaluate their intelligence.
Fair enough. I guess I'm just more optimistic about the potential of deep learning. I think it's a powerful tool that can be used to solve a wide range of problems, and I think it's just a matter of time before we figure out how to unlock its full potential.
Well, I certainly hope you're right, but I think we need to be realistic about the limitations of current approaches and explore alternative architectures that are more biologically inspired.
Agreed. I think the future of AI lies in hybrid systems that combine the strengths of different approaches. We need to find a way to integrate symbolic reasoning with neural networks to build AI systems that are both powerful and interpretable.
And I think the key to that integration is a better understanding of how the brain represents and manipulates information in different coordinate systems. Once we can crack that nut, I think we'll be well on our way to AGI.
Okay, so let's say we accept the premise that LLMs, while impressive, might not truly understand text games in the way a human does. Let's dive deeper into the science behind why that might be the case. What are the specific limitations of the algorithms themselves?
Well, one major limitation is the lack of a grounding mechanism. LLMs are trained on text data, but they don't have any direct experience of the real world. They don't have bodies, they don't have senses, they don't have the ability to interact with the environment. So their understanding of language is purely symbolic. It's not grounded in sensory experience.
Right. Think about the word apple. A human understands that an apple is a red, round fruit that you can eat. They have a sensory representation of an apple, a motor representation of picking it up and biting into it. An LLM, on the other hand, only knows that an apple is a word that's often used in conjunction with other words like fruit, red, and delicious. It doesn't have any of that embodied knowledge.
And that lack of grounding affects their ability to reason about the world. They can manipulate symbols according to the rules of language, but they can't connect those symbols to real-world objects and events. They can't use their knowledge to solve problems in the physical world.
But there's research being done on incorporating visual and other sensory data into LMZ. Multimodal learning is a big area of research right now. The idea is to train models on both text and images, or text and audio, so that they can learn to associate words with sensory experiences.
That's definitely a step in the right direction. But even multimodal learning has its limitations. The models are still learning correlations between different types of data. They're not necessarily learning about the underlying causal relationships.
And that's where symbolic AI can help. By explicitly representing causal relationships, we can give AI systems a deeper understanding of the world. For example, we could represent the fact that if you drop an object, it will fall as a rule in a symbolic knowledge base.
And that rule could be applied to a wide range of situations. The AI system wouldn't have to learn from scratch every time it encounters a new object or a new environment. It could use its existing knowledge to reason about the situation and make predictions about what will happen.
But building those symbolic knowledge bases is a huge undertaking. It requires a lot of manual effort, and it's difficult to keep the knowledge base up to date. And there's also the problem of common sense knowledge. How do you represent all the things that humans just know implicitly?
That's a challenge, but I think it's a solvable one. We can use machine learning to automatically extract symbolic knowledge from text and other data sources. And we can use ontologies and other knowledge representation techniques to organize and structure that knowledge.
And we can also learn from the brain. The brain is incredibly good at representing and manipulating knowledge in a hierarchical way. Different brain regions specialize in different levels of abstraction, and they communicate with each other to solve complex problems. Maybe we can build AI systems that mimic this hierarchical structure.
And that brings us back to the issue of coordinate systems. The brain represents the world in multiple coordinate systems, each of which is optimized for a different purpose. For example, the visual cortex represents the world in terms of spatial coordinates, while the motor cortex represents the world in terms of motor coordinates. And the brain is able to seamlessly translate between these different coordinate systems.
So you're saying that LLMs are limited because they only operate in one coordinate system, the textual domain?
Exactly. They can manipulate text according to the rules of language, but they can't connect that text to the real world. They can't translate between textual representations and other representations, such as visual representations or motor representations.
And that's why they struggle with tasks that require common sense reasoning or physical understanding. They don't have the ability to ground their knowledge in sensory experience or to translate between different coordinate systems.
So, to build truly intelligent AI systems, we need to focus on developing algorithms that can represent and manipulate knowledge in multiple coordinate systems. We need to find a way to bridge the gap between symbolic AI and neural networks and to build systems that are both powerful and interpretable.
Okay, I'm starting to see your point. But even if LLMs don't have true understanding, they're still incredibly useful. They can be used to automate tasks, to generate creative content, to answer questions. And they're getting better all the time. Shouldn't we focus on leveraging their capabilities rather than trying to build something completely different?
I agree that LLMs are useful tools, but I think we need to be careful about overstating their capabilities. They're not truly intelligent, and they're not going to solve all of our problems. We need to be realistic about their limitations and focus on building AI systems that are more robust, more reliable, and more trustworthy.
And that requires a more ethical approach to AI development. We need to think about the potential consequences of our work and to ensure that AI systems are used for good rather than for harm. We need to be transparent about how AI systems work and to give people control over how they're used.
And we need to be mindful of the potential for bias in AI systems. If the data that's used to train AI systems is biased, then the systems themselves will be biased. We need to be careful about the data we use and to ensure that AI systems are fair and equitable.
All right, so we've established some potential limitations. Let's zoom in on the mechanistic level. What specific algorithms or architectural choices within LLMs contribute to these shortcomings when it comes to truly understanding and playing well in text games? And how do we know this? What experiments or analyses reveal these limitations?
I think the attention mechanism, while powerful, can also be a source of superficiality. LLMs can identify which words are most relevant to a given task, but they don't necessarily understand the relationships between those words. They can focus on the keywords, but they might miss the subtle nuances of meaning.
Right, it's like highlighting the most important words in a paragraph without actually understanding the paragraph itself. You can identify the key terms, but you don't necessarily grasp the overall argument.
And the reliance on massive datasets can lead to overfitting. LLMs can memorize patterns in the training data, but they might not be able to generalize to new situations. They can perform well on the tasks they've been trained on, but they might struggle with tasks that are slightly different.
But there are techniques to mitigate overfitting like regularization and dropout. And the models are constantly being improved. Researchers are developing new architectures and new training methods that can help LLMs generalize better.
Those techniques help, but they don't address the fundamental problem of lack of understanding. LLMs are still learning statistical correlations. They're not learning about the underlying causal relationships.
And that's why they struggle with tasks that require counterfactual reasoning. They can't imagine what would have happened if things had been different. They can't understand the consequences of their actions.
And that's also why they struggle with tasks that require planning. They can't anticipate the future and make decisions that will lead to a desired outcome. They can only react to the present.
Okay, but let's talk about specific experiments that demonstrate these limitations. Are there any studies that show that LLMs struggle with counterfactual reasoning or planning in text games?
There's a growing body of research that suggests that LLMs struggle with these kinds of tasks. For example, some studies have shown that LLMs are easily fooled by adversarial examples, which are slightly modified inputs that cause the model to make incorrect predictions.
And other studies have shown that LLMs struggle with tasks that require them to reason about the beliefs and intentions of other agents. They can't understand that other people might have different beliefs or that other people might be trying to deceive them.
And still other studies have shown that LLMs struggle with tasks that require them to transfer knowledge from one domain to another. They can perform well on the tasks they've been trained on, but they can't easily adapt to new tasks.
Okay, those are valid points. But I still think that LLMs are a valuable tool for many tasks, and I think that their limitations are being actively addressed by researchers. I'm optimistic that we'll eventually be able to build AI systems that have true understanding, and that can perform at a human level in a wide range of tasks.
I hope you're right, but I think we need to be realistic about the challenges that lie ahead. Building truly intelligent AI systems is a very difficult problem, and it's going to require a lot of hard work and innovation.
Agreed. And we need to be mindful of the ethical implications of our work. We need to ensure that AI systems are used for good and that they're not used to harm people.
Absolutely. We need to be responsible in our pursuit of AGI and to ensure that it benefits all of humanity.
All right, ethical considerations firmly in place. Let's say we're a team of researchers tackling this LLMs and text games problem. Based on everything we've discussed, what are some specific research directions we should pursue? What experiments should we design? What algorithms should we develop to address the limitations we've identified?
From a neuroscience perspective, I'd like to see more research on how the brain represents and manipulates symbolic information. How do neurons and brain regions contribute to cognitive functions such as language comprehension and strategic decision-making? Can we identify the neural correlates of understanding and use that knowledge to build more biologically inspired AI systems? A study on the correlation between specific neural pathways in primates and the development of hierarchical reasoning abilities could reveal key biological mechanisms for replicating such abilities in AI. This may enable neuro-symbolic algorithms to encode both the factual knowledge and flexible reasoning that characterizes human gameplay.
I'd focus on developing better neuro-symbolic algorithms. Algorithms that can seamlessly integrate the pattern recognition strengths of neural networks with the reasoning capabilities of symbolic AI. How can we design algorithms that leverage hierarchical structures and rules to represent knowledge in a way that is both robust and easily manipulated for problem solving, rather than relying on massive datasets for statistical correlations? The true key to bridging the gap between symbolic AI and deep learning seems to be in carefully designing and connecting these representations. This hierarchical model needs a stronger logical foundation to make real progress towards more robust AI.
I'd want to explore techniques for representing and manipulating information in different coordinate systems. How can we build AI systems that can translate between textual representations, visual representations, and motor representations? How can we model the relationship between different coordinate systems explicitly? Perhaps AGI isn't just brute forcing complex patterns in massive datasets, but in explicitly modeling the relationship between different coordinate systems. If we could capture those relationships accurately, maybe we wouldn't need to rely on such an extensive amount of data to achieve intelligence. I suspect the core algorithm needs to be able to translate between different coordinate representations.
From my perspective, I'd double down on improving deep learning architectures and training methods. How can we make LLMs more data efficient? How can we improve their ability to generalize to new situations? How can we make them more robust to adversarial examples? The progress in accelerating deep learning hardware, like specialized GPUs and TPUs, is remarkably impressive. The ability to process trillions of parameters in real time demonstrates the potential of this approach to AGI. I'd investigate the possibility of discovering novel, more efficient data compression methods that further enhance learning from data.
And specifically, thinking about those architectures, I wonder if we can bridge the gap between the abstract representations used in hierarchical reasoning and the low-level sensor and motor data used by neural networks. Perhaps a neuroscientifically inspired method that translates between symbolic and neuronal codes could provide a more accurate and robust method of knowledge representation in AI.
And that ties back into the need for better explainability. How can we make these AI systems more transparent? How can we understand why they're making the decisions they're making? That's crucial for building trust and ensuring that AI is used responsibly.
Yes, explainability is key. If we don't understand how these systems work, we can't be sure that they're making decisions based on sound reasoning. We need to be able to audit their decisions and identify any potential biases or errors.
And I think that explainability can be achieved through better visualization tools. Tools that allow us to see what's going on inside the model, to understand how it's processing information. That can help us to identify areas where the model is struggling and to develop new techniques to improve its performance.
So really, a multi-pronged approach, better understanding of the brain, better algorithms that combine the strengths of different approaches, and a commitment to ethical development and explainability.
Sounds like a plan. Now we just need the funding and the time to make it all happen.
And a few breakthroughs along the way wouldn't hurt either.
I think we're closer than we think. The pace of progress in AI is just staggering. I wouldn't be surprised if we see some major breakthroughs in the next few years.
Well, let's hope so. The potential benefits of AGI are enormous, but we need to make sure that we're developing it responsibly and that it's used to benefit all of humanity. All right, well, that's all the time we have for today. Thanks for joining us for this cognitive spirals exploration.
Yeah, thanks for the insightful discussion. Always a pleasure.
Indeed. Until next time.
Goodbye, and keep thinking.